It's a great pleasure and honor to be here. Let's begin with a quick show of hands. How many of you remember the 1985 movie trilogy, Back to the Future? Anyone? Almost everyone. Okay, fantastic. Well, for those of you who were born after 1985, Back to the Future is about time travel. And if you're excited by time travel, you will love the field of causal inference. Causal inference is the branch of statistics that's concerned with effects, with the consequences of our actions. And that's really important because identifying one causal law in your data can be more powerful than dozens and dozens of correlational patterns that you might find. It's why causal inference has been at the heart of statistics for a long time. And it's why no big data approach and no modern approach to data science can be successful without an understanding of causal effects. So in this session, I want to make sure that each and every single one of you walks out with at least a basic intuition of what it means to estimate a causal effect and what our main tools are. Now, the main gold standard method for estimating causal effects is a randomized experiment. It's pretty obvious to us nowadays. It's only been formalized about 100 years ago. But in lots of situations, we can't run a randomized experiment because it's too expensive, or too difficult, or unethical, or because it simply wasn't done. And in all of those situations, we want to have a handle on getting an estimate of causal effects, even in the absence of an experiment. My name is Kay Brodersen, and in this session, I'd like to focus on a particular tool that we've been developing and using at Google called CausalImpact. Now, let's start with a simple example. Some of you might remember what happened on the 15th of January last year. On that day, in the morning at around 9 a.m., the Swiss National Bank decided to release the peg between the Swiss franc and the euro. And what had been an incredibly stable exchange rate for years, all of a sudden, within minutes, became subject to the free forces of the foreign exchange markets. Now, from a causal inference point of view, the question that we want to answer is, what was the effect of publishing that press release? And the answer is pretty simple, because we would probably all agree that this is what would have happened to the exchange rate had that press release not been published. In the language of causal inference, we have our observed data, Y1, and all we need to do to understand causal effects is to estimate the counterfactual, Y0, what would have happened in the absence of the action whose effects we're interested in. Abadi and colleagues have introduced the term synthetic control, popularized that term, since we don't really have an experiment, there isn't really a control in the experiment sense, and yet we want to be able to estimate something that looks just like a control. That's important because the difference between the counterfactual and the actual observed data is our causal effect estimate. And as a sort of rule of thumb, whenever you draw a causal effect in a time series chart, you want to draw it as a vertical arrow. Whenever you see horizontal or diagonal arrows, they're almost always wrong. Now, in real life, things don't always look as clean as they are here. So your time series of clicks or conversions or sales or downloads might look more something like this. Something that has erratic patterns, trends, day-of-week patterns, month-of-year seasonal variations. And yet the same thing holds. We want to be able to estimate what would have happened to our clicks or downloads or sales in the absence of the action that we're interested in. So again, we want to be able to compute that blue counterfactual that you see here so that we can look at the difference between what actually happened and what we think would have happened. The tool I'd like to acquaint you with is called CausalImpact, and it's something we've been developing and using for a while at Google. And what I'd like to convince you of is that you can run these kind of analyses that you saw on the previous slide in just 3 lines of code. So we'll work our way towards that. Before getting to that, let's take a step back and sort of remind ourselves of what a causal effect really is. So the problem of causal inference begins with a treatment. This could be a product release, or the beginning of an advertising campaign, or a change in your terms and conditions. anything that interacts or interferes with the market that you care about. Now, there's two things you can do. You can either administer the treatment, take the action, make that change, or release that product, in which case we get to observe the potential outcome under the treatment. Or you could decide not to take the action, in which case we get to observe the potential outcome under no treatment. Now, the causal effect of the action is the difference between two potential outcomes. And as you can already intuit from this slide, we can't take both actions at the same time. We can't release the product and not release the product. We can't change our terms and not change them at the same time, which means we can't ever observe both potential outcomes at the same time. And that means that we can't ever observe a causal effect. We can never ever observe a causal effect because we can't observe both potential outcomes at the same time. So the only options really are to either run an experiment where we observe some of the potential outcomes under the treatment and some under no treatment, or to use what statisticians refer to as observational methods, observational analysis methods, to try and understand and estimate causal effects in the absence of an experiment. That's going to be the focus today. There's one exception, perhaps, and that returns to the Back to the Future movie that we started with. If we could travel back and forth in time, all of this wouldn't be a problem. We could go into the future. In the movie, by the way, in case you're wondering whether any of this came true, just look at your photographs from last year. That's the year that was the future in Back to the Future. So we could go into the future, purchase something like a sports almanac containing the sports betting results of the past 50 years, go back into the past, and observe both potential outcomes. The first one is the original, where Biff Tannen is not particularly successful, sort of getting by, versus the alternative potential outcome, where Biff Tannen is a ultra-rich real estate tycoon sitting here in his Tannen Tower. Now again, the causal effect of taking that almanac back into the past is the difference between these two potential outcomes. And the movie shows us that if only we could travel back and forth in time, we could observe both of them, and therefore get an exact observation of the causal effect. Now, a helpful framework for thinking about causal effects on our way to making this slightly more formal is the so-called potential outcomes framework. It's an idea that's been developed and popularized by Neyman, Rubin, Holland, and Imbens, and many others. And it sort of starts with a simple table. If there's one slide for you to remember from this session, let it be this one here. So in this table, every row is an experimental unit. For example, in a clinical trial, this will be a patient. In a psychology experiment, this will be a healthy subject. In a web traffic experiment, this will be a cookie or a user. And in an advertiser experiment, this could be an advertiser. Now, the first thing we'll note down is, for all of our units of treatment, is the treatment status. So 1 for treatment group and 0 for control group. So in a randomized experiment, that column would be randomized. You would have allocated units to the treatment group in a randomized fashion. And now the trick really is to distinguish between these two potential outcomes: the outcome under the treatment, yi1, and the outcome under no treatment, yi0. So you can see from this table that we know what the treatment group looks like under the treatment. Those are the ticks. But we'll never ever know what the outcome under the treatment would have looked like for the treatment group if they hadn't, for the control group if they had been treated. And those are the question marks. And vice versa, we'll never ever know what the treatment group would have looked like had they not received the treatment. And then finally, there's often other variables which are sort of fixed characteristics of our units, which I'm just collectively referring to as covariates here. These are things that we often measure during the pre-period before the experiment. Now, sometimes you might see people analyzing an experiment by running something like a t-test or an ANOVA. And what they're doing in that case is they're comparing the observed outcomes in the treatment group to the observed outcomes in the control group. And that's fine. However, oftentimes we can get more flexible and statistically much more powerful estimates by taking a different approach, by actually estimating each of the potential outcomes that are missing. In other words, if we complete that table with an approach known as imputation, we're getting an estimate for all the missing potential outcomes, and we can then just read off our causal effect estimate directly from that table. Now, this is something that works beautifully well in a randomized experiment. But as we said at the beginning, there are lots of situations where you can't run an experiment because it's too expensive or too difficult or unethical, or it simply wasn't done. In those cases, our world looks a bit more like this. We sort of have one market that we care about, and that market is treated. We've already shipped our product, we've already changed our terms and conditions, or we've already launched that advertising campaign everywhere. So we know what happened. What we don't know is what would have happened had we not taken this action. So our strategy here is going to be to estimate that counterfactual yi0 and then just compare the two. So all of the machinery is going to go into estimating that counterfactual using statistical models, deep learning models, you name it. Inference is going to proceed by doing this repeatedly. So on the first iteration, we get one estimate, and we repeat that across iterations so that across all of these iterations, we get a distribution of our causal effect, because that's really what we're interested in. A distribution that tells us, here's our posterior mean, a point estimate of the causal effect, and we can use that same distribution to quantify something like a credible interval or a confidence interval about our effect. Now let's make all of this concrete by going back to our example. So in this time series, the only thing that we know is that we did something to the market on the 1st of January 2012. Okay, that's where we launched the product or the campaign. That splits our time series into these two parts, the pre-period and the post-period. And what we want to do is compute an estimate of the counterfactual, an estimate of what would have happened had we not taken that action on the 1st of January. And a proper statistical approach demands that we compute not just a point estimate, but through these iterations, through these repeated simulations, we get a credible interval around those predictions, telling us the degree of uncertainty that lie in our predictions. Now, you might ask, how would we ever come up with such a specific prediction of the counterfactual? And the trick really is to use other time series which are related to our outcome of interest. So here are two examples. Red and green are other time series which are themselves not affected by the treatment, but which are predictive of our outcome. For example, web searches for our industry, or web searches for our competitors' products, or the stock market, or even the weather. All of these can be useful time series that are correlated with our outcome of interest, yet they're not directly themselves affected by the treatment. That makes them great predictors. For example, in this case here, you can see that whenever the green time series goes up, so does the black one. And similarly, the red time series has this holiday spike just before the end of the year. And again, you can see that in the black time series as well. So here's our strategy then in a nutshell. We want to train a model, a statistical model, a machine learning model, any kind of model really, to learn that relationship in the pre-period. Learn the relationship between how we can explain black as a function of red and green. And then we're going to apply that model in the post-period. And that prediction is going to give us our counterfactual estimate. So we train our model in the pre-period and then apply the model in the post-period. That's the entire idea behind synthetic control estimators. Now, I'm just pushing that plot to the top of the slide. And what I'm showing at the bottom in the second panel is the difference between the observed data and the counterfactual. And you can see that this represents our pointwise causal effect, and it's sort of hovering around 0 in the pre-period, and then shooting up right after the action was taken and decaying back down. Now, in this case, I injected a causal effect here, just for illustration. And the true causal effect in this example is what you can just about see by the green solid line in the second panel. All of that goes to show that, in this case, the method correctly recovered the true causal effect from the noisy data. As I mentioned, you can use any model here, and the particular modeling approach that we prefer in this case is a family of models known as Bayesian structural time series models. But this could be any other model. So the model that I've used here on the previous slide is what you see here as a graphical model representation, distinguishing between observed data and latent states. This is the kind of model that's implemented in the CausalImpact tool, but you could use any other model as well. Now let's take a look at a concrete example. Google AdWords connects users and businesses in all those cases where the best answer to a search query might be a business, like your business. So an obvious application then for a tool like this will be to ask, well, how did my advertising campaign perform? How well did we do? Was it worth the spend? So here's an example of an advertiser who started an advertising campaign in week 0 of this time series chart. The black solid line is the number of clicks this advertiser got on every day in the US. And the blue dotted line is our counterfactual estimate. This is telling us this is how many clicks this advertiser would have gotten every day had they not run this advertising campaign. And if you sum this up over the 6 weeks during which the advertising campaign was run, you end up with about 85,000 clicks. That's the incremental effect of the campaign. Now, you might ask, well, how do we know that these are accurate estimates? And that's an important question. But we need to make sure that we validate these sort of methods against cases where we have ground truth. And one way of doing that is to run a randomized experiment. Go back to that world where everything is clean and controlled and simple. And in fact, that's what this advertiser did. So only half of the US were targeted by this campaign. The other half were exempt. And so the second plot here shows how you would have traditionally analyzed this sort of data, where the black solid line shows the number of actual clicks, and the blue dotted line shows the number of clicks in the control group, which didn't receive any advertising. Now, the fact that these two panels look almost identical tells us that in this case, the method did an incredible job at estimating how many clicks we would have had without the campaign, even without any access to an actual control group. CausalImpact is a tool that we found really helpful in our own analyses, and that's why we decided to make it available as open source software. So CausalImpact is available on GitHub. There's a blog post describing it, and there's a paper that goes into a lot more detail about the methods underlying the tool. But let me show you in practice how this works and how each and every single one of you can run a CausalImpact analysis in a couple of lines of our code. Okay, so in this case, I'm looking at our studio here, and I've prepared a little toy data set, which I'm just going to load into my R session. So this is a data set of 100 observations with an outcome variable called y and a single predictor time series called x1. In practice, you would typically have a handful or perhaps even dozens of these predictor variables, and the tool uses a spike and slab prior to automatically find out which of these predictors are useful. Let's take a quick look at these data. So this is what the data looks like. The black solid line here is the actual observed data over time, and the red dotted line is our predictor variable. Now you can see that the two are really correlated in the pre-period. So that's a great kind of setup for this analysis. And then you can see that they sort of diverge in the post-period after time point 70. Time point 70, that's the point where we took our action. Now, we could probably all sort of draw roughly what we think would have happened to black in the absence of the treatment. Perhaps it would have gone down slightly, since that's what the dotted red line is doing. But we really want to formalize that so that we can not just convince ourselves, but also convince our colleagues or customers of this kind of analysis. So the only thing I'm going to specify here is the pre-period and the post-period, indicating that time point 70 was the date when we started our action. And that's really the only thing that's needed to run this most basic kind of analysis. You could go a lot further go into more complex models, I think it's important that the entry barrier is extremely low. So that's the only thing that we need to run a causal impact analysis, providing the data and indicating the pre and the post period. And in this time that just elapsed, what the tool did is inspected the data, constructed a Bayesian structural time series model, used a Gibbs sampler for posterior inference, and summarized all of the results in this impact object. So let's take a look at this object. So I can just run the plot function on this, and this is returning a ggplot object, so I can interact with it in the usual way, for example, to increase the font size. Okay, so let's take a look at this. Okay, so this plot shows us 3 panels. The top one is the original time series and our counterfactual estimate. And it sort of maps our intuition that the time series would have meandered down slightly in the absence of the treatment at time point 70. The second panel shows the difference between your observed data and the counterfactual estimate. That's really our point-wise causal effect. You can see it's around 10. And then finally, the third panel is something that makes sense for summable flow quantities, like clicks, conversions, or sales, where we're just adding up these causal effects over time, so we get a cumulative causal effect that's around 300 by the end of the treatment period. If you care about a quantitative summary of what we just saw here in these plots, you can just call the print method on this object, and you get this table that tells us what was the actual activity like, what would the activity have been like without our action. And those are really the kind of numbers that you'd want to summarize in a report. Now, if you're anything like me, and you have a sort of healthy disregard for actually writing down these reports in prose, then I recommend this command over here, which I'll just copy and paste, which gives you a nice sort of prose summary telling you what you just did, what the data were, what the results looked like, and how to interpret them. With that, let me take a moment to thank the many colleagues and friends who've been involved in this work at various stages during the development cycle, in particular Steve Scott, who is the author of the BSTS package that CausalImpact is based on, as well as Alain, Lars, Nicola, Penny, Fabian, Simon, Rowan, and Hal, all of whom have been really strong supporters and contributors to this work. And with that, finally, let me thank you for your attendance and attention. Thank you.
Thank you, Kay. I don't know how you managed to make simple what is a pretty challenging problem. Any questions for Kay, please? Yes, Paco.
One question would be, where do we go to look for the other time series to use? Are there repositories for these?
The question is, where do we get these other time series from, these predictor time series? That's really where you as an analyst want to focus your energy on, rather than on the modeling mechanics themselves. So that's what this tool tries to do. In practice, other countries are often a great source of getting controlled time series. Markets where you didn't take your action. The stock market can be a great resource. Indices like employment labor market indices. The weather can be a fantastic predictor because it's arguably one of the things that is definitely unaffected by whatever we do to our markets. Google Trends is a fantastic source of time series. Google Trends is something that you can access and look for the number of search queries we got for any concept you like over time. And often we see Google searches as sort of the unmoved mover in our analyses, things that come in that indicate, for example, an interest in our industry or our products without being directly affected or moved by the actions that we take.
It seems to me that being able to measure the impact of an investment, in this case an advertising campaign, makes it pretty trivial to derive or calculate the return of investment of any campaign, for instance. Have you seen any interest following the publication of your paper to build tools around this library?
I think it's a great question. I think the extending this analysis, taking the results, and then basically dividing your impact by your investment is the natural step that you'd almost always want to take based on the results. We've been really excited and amazed by the breadth of applications we've seen in fields that we had never thought about after we open sourced this tool. And return on investment analysis is a great example of that.
Okay, anyone else? Yes.
I think it's on the terms of the previous question. How do you prevent for finding a spurious correlation for all those control time series? What are some best practices?
It's a great question. How do you prevent finding spurious correlations? Imagine you stick in hundreds and hundreds of time series. There's always going to be some that perfectly correlate with the outcome variable in the pre-period. The best safeguard against this is to backtest your method in the past. So for example, just before you actually run the analysis on your period of interest, test your analysis in the past where you didn't take any actions and verify that the tool correctly tells you that there was no effect. So backtesting the analysis is a great way of validating that your method works and doesn't pick up spurious correlations.
Anyone else?
I think over here.
Who have the microphone?
Hi. Do you have a method to decide how many time series do you need to understand the impact? Because in the example, you have 2 time series in the first example. Then in the R example, you had 1. Do you have some way to decide if 1 is enough, if you have 2, if with 1 is enough? I don't know if it's clear the question.
It's a great question. How many predictor time series would you typically want to use? I think as a rule of thumb, the best analyses I've seen use something between 5 and 20 time series. It's sort of an amount that's manageable. You still understand what each of these time series means, rather than throwing in lots and lots of potentially spuriously correlated series. And at the same time, this toy example that uses just 1 time series, that's really a toy example. You wouldn't want to use that in practice, because you'll be completely at the mercy of that 1 time series. So what often happens is that in one of those time series, there might be spikes and dips that you see. And without other time series to guard that, you'll be really relying on exactly what that 1 time series did. So in practice, using a handful or perhaps a dozen or 2 dozen of time series is typically the thing that works best.
Yes.
Hi. Can you use this method to calculate the impact of multiple events? I mean, if they even overlap in time?
Can we use this method to analyze multiple events that overlap in time? That's a really interesting and I think mostly open research question. I'm really interested in this question. I'd love to chat with you afterwards.
Very good. So, sorry, Paco.
One question. It seems that the forecast that you make, the package makes, is somewhat at the mercy of the confidence intervals. Are there tools for being able to analyze what is contributing to say the width of the confidence interval during that post-treatment or during that treatment period, and maybe get in and try to reduce it?
Mm-hmm. It's a great question. Statistical power is really directly related to how wide your confidence intervals are. If your confidence intervals are too wide, for example, if we go back to this case here, at some point, the longer you predict into the future, the wider your confidence intervals get, reflecting this intuition that the further out our predictions are from the actual observed data, the more uncertain we should get. There are lots of things that contribute to this. The better your predictor time series explain your outcome, the tighter your CIs. The less noise, the less state noise or observation noise there is in your outcome time series, the more stable your predictions will be. typically the more predictor time series you have, the tighter your CIs will get. So there's a bunch of factors that go into this. On the flip side, if you don't have any predictor time series with strong predictive power, then your results will just reflect that. They will just tell you there's nothing we can say, it's just too uncertain.
Okay, very good. Lots of questions. Thank you very much, Kay. It's been awesome. Kay. We have 45 minutes for lunch break. Thank you.